In this video, we're going to talk about percentage uncertainties and show you how to calculate them and to refine the experimental design to lower those percentage uncertainties. Now, percentage uncertainties, it is the absolute uncertainty as a proportion of the measurements. That's a difficult definition to try get your head around. But essentially, it is calculating how wrong the final value will be according to the percentage, according to the uncertainties or the errors you have in each bit of equipment you have. So this is dependent totally on the apparatus that you have. So if we look at the calculation, which is the most important thing because that's where most questions are going to be on, the percentage uncertainty is the uncertainty of the piece of apparatus times the number of readings that you take divided by the measurement. So what is a reading? So a reading is the value taken when you make a judgment. So if you look at a piece of equipment, for example, a measuring cylinder, and you fill it up to 50 and you look at it, well, your reading is that 50 centimeters cubed and your number of readings is 1. So your number of readings is 1. Okay. Now that is the same for a measuring cylinder or a pipette. You both just look at the level they get to and then you say, right, okay, there's 25, there's 50 centimeters cubed. Now with a burette, a mass balance and a thermometer, you're looking for changes. So you're looking for change in volume in a burette, change in volume in mass, change in mass, for a mass balance, or change in temperature for a thermometer. Now what is the measurement? The measurement is the value taken as the difference between the two readings. So for example, if I have two readings on a mass balance, it's that difference between the two masses that I have. If it's only one reading, it's just the volume that you've measured. So if it's a 25 centimeters cubed pipette, your measurement would be 25 centimeters cubed. If it's a 50 centimeters cubed measuring cylinder, your measurement would be 50. Now we're going to go through some typical percentage uncertainties because they can ask you, they don't often ask you, but they can ask you to work out an uncertainty of an actual piece of equipment. So first of all, when you're doing your readings, if you look at an analog graduated scale, that sounds complicated, but all it really means is a bit of glassware, usually that you look at the level to which the liquid has gone to and then read it off, or a thermometer when you're reading off the values. It's an analog and a gradual scale. Normally the uncertainty is assumed to be half the smallest graduation. So again, most likely, very, very likely, you will just be given the uncertainty. But if you're not given the uncertainty, you need to look. In an analog graduated scale, you need to look at the smallest resolution, or the smallest graduation, which is 1 centimeters cubed, for this 50 centimeter cube measuring cylinder, and then you just need to half that. So therefore, the uncertainty for that will be 0.5 centimeters cubed. But again, it depends on the size, which is why they normally give you the uncertainty in the question. Now a burette, well, that normally measures to the nearest 0.1 centimeters cubed, therefore the certainty will be 0.05, half of that. Thermometer, to the nearest 1 degree, therefore the uncertainty can be 0.5. 25 centimeter cube pipette, that's normally stated on the pipette. So if you're doing this in a lab, you will see it written on the pipette. Normally they can have class A or class B, and we'll talk later on in the video about the difference between a class A and a class B bit of equipment. When using a digital apparatus, and really the only digital apparatus we use in chemistry on a regular basis is a mass balance, okay, and that will just be the resolution, as in the lowest smallest graduation, and that is 0.01 on almost every balance you're ever going to use in a school. Now, let's put that all in a bit more of a graphic way and make it a little bit easier. So if you look at these, I've now simplified it, and now I've got all of my apparatus and I've got all of my uncertainties listed. Okay, and I've got my pictures. You can see my mass balance, you can see my measuring cylinder, my burette, my thermometer, and my pipette. If we just rearrange those right now, and we can see that the ones across the top are one reading. So I just look at it and I take off what the volume is when it comes to a measuring cylinder. I just look at the pipette and I know it'll be 25 centimeters cubed if it's a 25 centimeter cube pipette, and so on. We've got all of our ones that are two readings. So two readings, 0 on the mass balance, two readings on the burette, two readings on the thermometer. And that is the most common mistake that you make in these questions, is you don't remember that there are 2 readings on these 3 pieces of equipment, so make sure you do. Now let's go over a question about 1 reading. So we can see that we've got one reading relates to the pipette, so we can see the pipette over there, okay, and that is 1 reading, so that then goes into our equation, and the pipette was used to measure out 25 centimetres cubed of acid, so that's our measurement, 25 centimetres cubed of acid. The uncertainty was 0.06, so we've got our uncertainty. Really important here, it says give the answer to 2 decimal places. Let's get that out of the way. And let's actually do our calculation. Notice, if you look over here, you can see that everything that we're going to use is highlighted in orange. So we've got 25 centimetres cubed as our measurement, and we've got our uncertainty of 0.06, and it's to 2 decimal places. So all we have to do then is go, right, we are going to calculate. So our uncertainty, as we said, was 0.06. We know the number of readings. The number of readings is 1. Okay. We know the measurement. The measurement is 25. Okay. And we know it's a percentage, so don't forget the percentage. Okay. So there is our calculation, and that equals, if you put it in the calculator, 0.24%. Okay. And that is the simplest version and the way in which you calculate percentage uncertainty when you have a piece of apparatus with 1 reading. So having done the calculation, it's important just to remind you again, measuring cylinder, pipette for 1 reading. Okay, let's go on to an example with 2 readings. That's mass balance, burette, and thermometer. Okay, so important again to remember those 3. Let's do an example using a burette. So this is normally part of a larger question, a titration question. They normally just put the uncertainty question at the end of a calculation on titrations. So here we have all of our data, which we'll have to sift through, and our question is, the uncertainty in each burette is 0.05, and it's really nice because it says in each burette reading. Okay, calculate the percentage uncertainty for the titer in titration 1. Now, it's really important there, you read titration 1. Sometimes people do it on the wrong titration, so read carefully. So if we rearrange all that around and we highlight our information again like we did before, we are doing this titration to titration number 1, okay, and we know our burette reading is 0.05, and we know there are 2 readings because it is a burette. So if we take that again, and we go, there we go for our, and we know our uncertainty is going to be 0.05, but the number of readings is 2, and that's the bit people miss. 2 readings, so I have to times it by 2. Okay, and then what I do is I divide that by the measurement. The measurement is the difference between the 2 values, which is 23.2. Okay, and then I times that by 100 to get my percentage. Okay, and that ends up being 4.31%. Okay, so we've got 4.31%. So that is an example of how to use a piece of apparatus with 2 readings to calculate your percentage uncertainty. The next stage is to compare percentage uncertainty of different apparatus. So if we show you a full exam question here, which is the enthalpy change of neutralization for this reaction, which is potassium oxide plus hydrochloric acid. We've got some mass readings that are given to us. We can see the mass of the bottle plus potassium oxide and the mass of the empty bottle. So it makes sense if I want to know the mass of the potassium oxide, I would take the mass of the bottle and the potassium oxide and take away the mass of the empty bottle from that. We also have the mass of the empty polystyrene cup that we're doing the reaction in, and the mass of the polystyrene cup plus a final solution. So if we want to know the final solution's mass, we might use these 2 figures. Now we're given the temperature reading, which is initially 19.5 and then finishes on 54.5 degrees Celsius. And then we're given some uncertainty measurements for the temperature reading and for the mass reading, so 0.05 and 0.01. Let now find out what the question is. So the question is, determine whether the mass of potassium oxide or the temperature change has the greater percentage uncertainty. So we're going to compare the temperature change and the mass readings. So let's try and simplify this all down so we can answer the question. And let's highlight the bits that are important. So we know it's the mass reading. The mass reading is of the potassium oxide. So it's only these two values we need. And we need those temperature changes. And we need the uncertainty values. So let's simplify this down even more and get rid of everything we don't need. So we've got our percentage uncertainty equation here. Okay, and we've got our data that we need. So let's start doing something. Well, the first thing we need to realise is how many readings we have. We've talked about in this video really being important how many readings we have. We need to know. So basically what we've got is 1, 2 readings there and 1, 2 readings there. So both have 2 readings. Now if we then put our uncertainty measurements back in, our thermometer 0.05, our mass balance is 0.01 as given by the question. Okay, now we know we've got 2 readings. Let's change our equation. So our equation now says times 2, okay, because we have 2 readings. So we now need to calculate the uncertainties for both of these readings, sets of readings. So let's do that. So to do the percentage uncertainty, we need the uncertainty itself, which we're given in the top right corner here, 0.05 and 0.1. And we need to do the measurement. We can do the measurement by taking these different readings and minusing them from each other. So the first one is the mass of potassium oxide being 1.24 grams. And then we do the temperature change. The temperature change is 35 degrees Celsius. So we have a measurement for both the temperature and for the mass balance. So all we do is we start putting it out. So therefore we have percentage, okay, uncertainty. And this percentage uncertainty is going to be for our mass measurement. Okay, so the percentage uncertainty for our mass measurement, if we look over here, we know that from up there our mass balance was 0.01. Okay, so that was 0.01. We know there are 2 readings. We know overall, if we look at that, our mass was 1.24 grams. Okay, so we've put that in. And we can see that if we do 0.01 times 2, and we do that divided by 1.24, and when we times that by 100 to get the percentage, we're going to get 1.61%. Okay, so we've got 1.61% for the first one. So that's our mass balance. If we do the temperature reading, again we do our percentage uncertainty. Okay, and this time it's going to be for our temperature. Okay, and again we look up and say, well, our uncertainty is 0.05. Okay, that's again times by 2 because we have 2 readings. We've been through that. And then our temperature change is going to be divided by 35. Okay, times that by 100 again. Okay, and if we times that by 100, we get 0.29%. Okay, so we get 0.29%. So if we're going to determine whether the mass of the potassium oxide or the temperature change has a greater percentage uncertainty, we can see that the mass reading is 1.61 and the temperature change is 0.29. So therefore the mass readings and the mass change has a far higher effect on percentage uncertainty. So we're now going to talk about the last question, which is reducing the percentage uncertainty. Now you need the equation for that, and if you look at the equation you'll see that it is calculated with the uncertainty divided by the measurement. So if we want to change the uncertainty and reduce the uncertainty, we need to change this value, the uncertainty, or this value, the measurement. So let's talk about the first way in which we can do that. So we can reduce the uncertainty of the apparatus, so change the apparatus and make sure it has one with a higher precision. That means it has a smaller graduated scale, for example, 0.1 centimetres cubed graduations instead of 1. An example of that is with a 100 centimetre cube measuring cylinder, and the 100 centimetre cube measuring cylinder can have, if it's a class A measuring cylinder, an uncertainty of 0.5. Now if you put that into the equation, you'll get 0.5% percentage uncertainty. Now, Class A is a more expensive piece of equipment, and you probably won't have it in your school. So therefore, we usually have Class B. Now, Class B has an uncertainty of 1 centimetres cubed. Now, if you put that into the equation, you get 1%. And as you can see, you have changed your percentage uncertainty from 0.5 to 1% by the use of a different measuring cylinder. This is the least likely kind of answer. We're going to go on now to talk about the most commonly questioned, and that is the measurement. So in the exam, this is much more likely than the example which you're going to get given. So if you want to change the measurement, you can therefore reduce the uncertainty of the apparatus. So the measurement is divided by, so we need to make that measurement larger. Okay, so if we make that measurement larger, we can reduce the uncertainty overall of the apparatus. The apparatus most commonly done for this is a burette. I've given the uncertainty here as 0.05. And the most common example is therefore titration. And we have to increase the titer to increase the measurement, because the measurement is the titer. Okay, so if we take an example of the titer being 25, remember there's 2 readings, so we have a 2 there. Okay, we get a 0.4% percentage uncertainty. But if we double the size, so we have 50, okay, double the volume of the titer, notice our percentage uncertainty goes down to 0.2 or 0.2. So if we change the volume of the titer, we can change the uncertainty. Now, the important thing is not just that we change that, is that how do we do that? It's really important, how do we do that? So if you want your extra marks in your questions, make sure you describe how. Now, we do that by reducing the concentration of the solution in the burette. So that means there's less moles per decimetre cubed, which means you need more decimetre cubed or more centimetres cubed to neutralise your solution in the conical flask. So make sure you mention both. I will increase the volume of the titer, and I'll do that by reducing the concentration of the solution.